Hi everyone, so this is lecture 7 of CHEN 430 Process Design 1. In this lecture, we'll start talking about heat and power integration and how to really optimize your heat exchange network, how to avoid wasting energy from hot streams and avoid wasting money on cold streams, right? So just a few announcements. So this is October 5th, week 7. We'll be covering heat and power integration 1 and Aspen Plus tutorial number 6. Aspen Plus tutorial number 5 is due this week. However, you have 2 weeks to submit it from the due date without any penalty. I added a new project deliverable draft. So, so project deliverable number 1 is due next week. Please send me a draft this week and let's set up a time for a group discussion with each of your groups. Okay, I just want to make sure that you're on track, you have the right idea, and you're approaching things correctly. Homework number 3 will be assigned today. Again, this is a very important homework. Your exam will primarily be from homework number 2, and homework number 3 will cover how to ordinary distillation sequencing and heat integration. Homework number 3 will also give you some very good practice to try and understand the concept we're going to cover this week. Okay, so let's get started. So the objectives of this lecture, that if I give you some data on some hot and cold streams from a process, you should be able to compute what is called a pinch temperature, and you should be able to compute a parameter called maximum energy recovery target. And there are 2 methods to do this. There's a graphical method, and then there's an algebraic method. We're going to go over them over the next 2 weeks. Okay, so starting off, let's have a look at this process right here, which is a motivating example. So I have stream here. It enters at 300 Kelvin. I have a heat exchanger. I heat it up to 550 Kelvin. Goes to an adiabatic reactor. From the adiabatic reactor, I have 2 streams. One is 520 Kelvin. I cool it down to 330 Kelvin for my final product. And then the bottom of the reactor goes to a separation unit, where the top of the separation unit is 380 Kelvin. I cool it again to 300 Kelvin. And then here I have a recycle process in which I have a cooling or a heating from 320 Kelvin to 380 Kelvin. And I'm going to denote this stream as C1, this stream as H1. Let me get the laser pointer here. This stream as H2, and this stream as C2. So when taking a look at this, is there something wrong with this process from an energy viewpoint? So, I'm doing some very big heat changes. Here I'm heating by 250 Kelvin. Here I'm cooling by about 200 Kelvin. Here I'm cooling by about 80 Kelvin. And here I'm heating by about 60 Kelvin. So, what's wrong is that why don't I use some of this, some of the heating requirement here and some of the heating requirement here and integrate them somehow? So, this stream needs to lose 200 Kelvin and this stream needs to gain 200 Kelvin. Is there a way for me to transfer the energy I need to remove from this stream and use it to heat up this stream? Why hasn't this been implemented? So there is no integration of energy. So this type of design does not have any energy integration, and it's a suboptimal design. So you need to be aware of this. And usually your base cases or your first sort of draft of your process won't have any energy integration. And this is something you need to look at in sort of a second step or a third step after you're happy with the base case, after you finalize all your temperatures. Now let's have a look. See, is there room for me to, use some energy from a hot stream, give it to a cold stream, all of this stuff. So this is called designing a heat exchange network, and we're basically dealing with this following problem. If you have a number of hot streams denoted as NH with a given heat capacity flow rate, each having to be cooled from a supply temperature to a target temperature, right? So again, just note the notation or the language we're going to use. Supply temperature, target temperature. Supply is basically the original temperature of the stream. Target temperature is the final temperature you want the stream to be at. So I have NH, number of hot streams. All of them have to be cooled. And I have a number of cold streams, NC. All of them have to be heated from a supply temperature to a target temperature. So how do I design the heat exchange network to maximize, the integration of energy between these hot and cold streams? So your design objective usually is you need to have an optimum network of heat exchangers connecting the hot and cold streams and um, the hot and cold utilities as well, right? So I need to design my heat exchange network or my heat integration network in a way where I maximize the energy recovery from the hot streams and from the cold streams. So there's always a trade-off when doing these things, right? And the trade-off in this case, you see it at the top of the slide here, capital versus energy, right? Which is money versus how much energy can I actually recover from these streams. And there's an optimal point, and this optimal point implies that there's a trade-off between the capital cost, which is the cost of equipment, versus the energy cost, which is the cost of utilities, or how much energy I need to buy for my process. So if I look at this design, so we said we have let's have a look here. We have a bunch of streams here. These are my hot streams. They come in at T in, they leave at T out, and I install 3 coolers on these 3 hot streams to cool them down. And then I have about 3 cool streams, and I install 3 heaters to heat them up. And the heaters are basically powered by steam, or not powered, or they get their energy to heat up the stream from steam, whereas the coolers use cooling water as a coolant to remove the heat from these streams which I need to cool. So if I set it up this way where I just install a heat exchanger at the end of each stream, so I have 6 heat exchangers, and does this really have the minimum equipment cost? Yeah, it does have the minimum equipment cost, because the alternative would be to install 9 heat exchangers, 1 at every intersection, right? However, this one has the highest energy cost, right? Or sorry, minimal energy cost. So if I install 9 heat exchangers, I'm gonna get the best energy recovery. I'm not wasting any energy. So I have my best energy integration. But if I only install heat exchangers, I have my lowest number of heat exchangers, so I have my lowest cost. So these are really the extremes, right? I have an extreme where I only install heat exchangers, capital cost is high, or capital cost is very low. And I have the other extreme where I install a lot of heat exchangers, where capital cost is high and energy integration is also high, right? So let me just write this here. That's easier to see. So I have this guy, I have 6 heat exchangers, which is the minimum number of heat exchangers. So in this scenario, basically my capital cost is low, right? And my energy cost is high, right? Because I don't use any of the energy already available in the streams. So on the other end of the extreme, I have this design in which I have 9 heat exchangers. So this is the maximum number of heat exchangers. And in this design, basically your capital cost is at its highest, and your energy cost or your energy loss is at its lowest, right? So your energy cost is high. So here, I'm really recovering all of the energy available in these streams, but I need to install a lot of equipment. So there usually is a solution somewhere in the middle where I don't need to, lose a lot of energy or not use a lot of energy or use a lot of utilities, versus the other extreme where I need to install a lot of heat exchangers, right? So we really need to find the solution, which is the optimal solution, which is somewhere between these two. In order to do this, there's sort of a procedure which we're going to cover. Okay, let's have a look at a numerical example to try and follow this a bit more. So now let's add some temperatures to these streams. I have 3 hot streams, which I'm cooling from 300 to 200, and I have 3 cold streams, which I'm heating from 50 to 150, right? And the heat for all these streams is 1, right? And again, in this course, this CP actually refers to mCp, right? So just be careful because, you know, in heat transfer, probably Q is equal to mCp delta T, right? In this course, I'm going to lump m and Cp into just one term, capital Cp multiplied by dt. Okay, so just something to note, and this is called, you know, we call it mass heat capacity. It's just mCp, right? So you know, you won't be given any mass flow rates. You'll just be given a Cp value, which lumps the mass flow rate with the heat capacity. Okay, let's go back here. So the Cp for all these streams is 1, so they're all the same. So if I try and calculate the Q for each stream, it's just Q is equal to Cp delta T. So I can calculate basically a Q, or the heat required for each of these streams, right? And basically, you know, since Cp is 1 and delta T in this case is 100, so the amount of heat needed for each of these heat exchangers is 100, and the amount of heat needed for each of these heat exchangers is 100 as well, right? So I need to remove 100 kilowatt, or whatever the unit is, from these 3 streams, and then I need to add 100 energy units to these 3 streams. Okay, so if you take a look at the design, you know, area is from your heat transfer course, area is equal to Q over U dot delta T log mean, right? And if I calculate all the area required for these heat exchangers, find out that the area is equal to 13.3. Okay, so now let's compare it to the other extreme. So in this case, I have, you know, 3 heat exchangers. So instead of installing, you know, instead of basically installing 9 of them, I'm just installing 3, and all 3 are doing the job. And in this case, the area of heat exchange is 20, right? And if you look in this case, what I did is basically I just integrated this, let's call this hot stream 1 with cold stream 1, right? I just integrated these 2 guys, and then I integrated hot stream 2 with cold stream 2, and then I integrated hot stream 3 with cold stream 3, right? So this is a numerical example, a motivating example, where you can look here and see, you know, the design area here is 13.3, and design area here is 20.4. So you need to make a judgment call on which is the better design, right? From a chemical engineering sort of a heat, from a chemical engineering design perspective, design B is the better design, right? Because even though you have, because basically even though you have a larger surface area, so these heat exchangers will be bigger. However, I have a smaller number of heat exchangers, so I only have 3 heat exchangers compared to 6 in this case. Plus, I'm not buying any utilities in this process. So in design A, I need to buy steam, I need to buy cooling water, and you know, these cost money, right? Plus the 6 heat exchangers. Whereas in this case, I only have 3 heat exchangers. I'm not buying any utilities. However, these heat exchangers are slightly bigger than the guys over here. Okay, so you see there's always a trade-off between capital and energy. However, you always need to go towards the more integrated design. You need to look at these parameters, all this stuff, take a look at the bigger picture. Okay, moving on. So let's just start with some definitions before we move on, basically. So again, we said the supply temperature and the target temperature. Supply temperature, you can think of it, or it is basically your initial temperature. And your target temperature is your final temperature, okay? H is your stream enthalpy. Q, you know, it's basically the heat, which has to be added to the stream or removed from the stream. Units is megawatt, so we're gonna stick to standard units. So it's almost always gonna be megawatt or watt. Just be careful when converting between megawatt, watt, kilowatt. You know, kilowatt is 1,000 watts, right? And the megawatt is 10 to the 6 watts. Okay, so just be careful of these. And then we said Cp is heat capacity flow rate, and it's your flow rate multiplied by your specific heat capacity. So this, you also need to know this. You know, we're lumping both terms together. Second definition we need to go over is the minimum allowable temperature driving force, the delta T min. right? And this is very important from a thermodynamic perspective. You're going to run into it a lot once you deal with heat exchangers in Aspen. But basically the idea is that if I have two streams and I'm doing some sort of heat exchange, whether it's in this direction or, in that direction, whatever it is, there should always be a delta T minimum between the two streams, right? So that I can maintain a driving force for this heat to cross, right? Because if there is no driving force, heat will not cross from one stream to the other. Logically, Q is equal to Cp delta T. If this delta T is very small, then there is no driving force. There's nothing pushing this heat to move from one stream to the other. Absolutely impossible, or this should never happen. You have a cross, the two streams cross. This is thermodynamically false, right? So don't even think about this. This doesn't happen. This is a sin, this is a joke basically. If basically both streams, for some reason they start, they have a point which is less than delta T min, then basically your heat exchanger won't work effectively, and you won't achieve your desired objective. Okay, so this case is just not possible. This case is not possible. You're going to end up with negative numbers and then strange things and just thermodynamically false. These two cases are usually what happens. You always need to maintain this delta T minimum. And if at some point your two streams are below this delta T minimum, then your heat exchanger is just not working correctly, okay? Good, let me get pen back, all right. So let's have a look at this minimum allowable temperature driving force. Let's look at a motivating example here. Which of the two counter-current heat exchangers illustrated below violate the minimum driving force of 20 Fahrenheit? So I have two cases. Case A, I have one stream entering at 50, leaving at 80, and one stream entering at 100, leaving at 60. So where do you calculate your minimum driving force? You calculate it. So let's label these guys. So this is T hot in. This is T hot out, right? Temperature hot stream in, hot out. This is T cold in, and this is T cold out. Likewise here, right? T hot in, T hot out, T cold in, T cold out. Okay, anyways, so in order to calculate the delta min, I need to either compare THN with TC out and TC in and TH out, right? I don't compare THN and TC in. I don't compare TC out and TH out, right? Because these are countercurrent. So just be careful. If you recall what your countercurrent heat exchanger looks like, very, very general, basically, overview here, right? So this is, and inside this, I have another basically cylinder here, or another cylinder, whatever it is, shell and tube, very rough design. This is TH in, this is TH out. I have TC in, and here TC out, right? And the two fluids flow in opposite directions. So in this case, fluid flows in this direction, and inside here, the fluid flows in this direction. So I need to compare THN with TC out and TC out or TC in with TH out, right? So if I look at THN with TC out, this is 20, so this is fine. If I look at TH out with TC in, this is 10, so I have a violation here. If I look in this case, TH in and TC out, this is 30, so this is fine. TC in, TH out, this is 20, so this is fine. Okay, so when looking at this, just be careful countercurrent or co-current. You know, if it's co-current, I'm gonna look at these pairs instead, right? If it's co-current, I have THN, TCN, TH out, TC out, right? So I'm looking at the two opposite pairs. Something to keep an eye on. So which of these two violates the delta T minimum 20 degrees Celsius? It's this guy, design A. And basically this design is not feasible, right? So exchanger A violates the delta T minimum constraints. Exchanger A is not feasible. So this exchanger will not achieve what you wanted to achieve. It's suboptimal. Okay, moving on to some definitions. Exchanger duty. So what's the duty of a heat exchanger? In order to determine the duty, I need to get my CP, right? So this stream I have a CP hot. This stream I have a CP cooled, right? So in this case, we're told the hot stream CP is 0.3, the cold stream CP is 0.4. And you can of course do it mathematically to check whether you're violating this delta T minimum or not. If you're not violating, you're good. And the way to calculate your heat duty is just CP delta T, CP delta T, right? And CP hot delta T hot must equal CP cooled delta T cooled, right? If they're not equal, then something's off. Take a look at your calculations, see your numbers. Maybe CP value you're using is wrong. Maybe you're missed out. You missed something with the delta T units. No, all of this stuff. Double check it. But the heat lost from this stream should be gained by this stream, right? Assuming perfect emissions. Okay, so this is called the duty. Q megawatts. It's the heat transferred. Heat transfer area. And you should have covered this in your heat transfer course. It's basically the area required. So what's the area required for which will allow me to achieve this heat transfer? And this area required depends on a parameter called your heat transfer coefficient. And your heat transfer coefficient really accounts for the, what material is being used to make this heat exchanger, right? So if I have a copper heat exchanger, I have a fin heat exchanger, I have a stainless steel heat exchanger, heat transfer coefficient will be different, so the area required will be different, right? And we're not really gonna look at this parameter in this course, but this is something you need to know. Okay, and then the equation, of course, is A is Q over U multiplied by delta T log mean, okay? So these are the definitions you need to know. So now let's move on to a simple example. So let's have a look at this guy here, this example here. So what's going on? Okay, let's have a look. I have a stream entering at 30, leaving at 120. It enters a first reactor here. I'm gonna call this reactor 1. And then from this first reactor, I have two products, this stream right here and this stream right here. The bottom stream enters reactor number 2, where second reaction happens, and then I have an output stream at 180. I cool it down to 80, and then both of the reactor outputs enter into a distillation column. The top of the distillation column leaves at 60. I heat it up to 100 and recycle it back to the reactor. And the bottom of the distillation column leaves at 130. I cool it down to 40, and this is my final product. Okay, so I have a lot of things going on, but for the purpose of this lecture, you need to just see that I have two heating steps. So I have one heating step with an enthalpy of 162, and a second heating step with an enthalpy of 160. And here I have one cooling step with an enthalpy of 100, and a second cooling step with an enthalpy of 180. So how do we start approaching this problem? You're also given another piece of information. You're told that you have the utilities available for you to buy. You have steam available at 150 degrees Celsius, and you also have cooling water available at 25 degrees Celsius. Okay, so I have these utilities, so I can use these. So I can just use steam, push steam through these heat exchangers and push cooling water through these heat exchangers, and this will give me completely non-integrated process, but does what we want. But I want to integrate this process. I want to integrate it. So what's the approach here? This is the approach. First step, you need to really tabulate the information you have. This is very important. So step one, I tabulate all the information I have. and you need to do this always. If I give you sometimes I'll give you this table, sometimes I'll just give you this diagram. However, before doing anything, you need to have this table. So just be aware that step one is always to tabulate your information in this manner. As you can see here, I have streams, so I labeled my streams H1, H2, C1, C2. I wrote my supply temperatures and my target temperatures. So let's have a look. H1 is this stream, is my hot stream, right? And I need to cool it to 80, so my supply temperature is 180. My final temperature is 80. H2 is this stream right here. It's hot, I'm cooling it from 130 to 40. C1 is this stream right here. It's cold, I'm heating it to 100, from 60 to 100. And C2 is this stream right here. I'm heating it from 30 to 120, okay? So T1, your stream numbers, your source temperatures, your target temperatures, your CPs, these are usually given most of the time. I'll give them to you in some form. Maybe they're written on the diagram or they're given in a table. And then immediately calculate the enthalpy required for each stream, right? And then this delta H again is CP delta T, right? And you'll see it's gonna make sense. 180 minus 80 multiplied by 1 is 100. 130 minus 40, this is 90. Multiplied by 2 is 180. 100 minus 60 is 40. Multiplied by 4 is 160. 120 minus 30 is what? 90. Multiplied by 1.8 is 162, right? Because you have, 90 plus 72 is 162. Good. So this is step one. I give you a diagram, I give you a table. You always need to get to this before doing anything, right? Okay. So in this example, you're being told to design a network of steam heaters, water coolers, and exchangers for the process streams where possible. Use exchangers in preference to utilities. So you're basically told to let's integrate this process to achieve what we want to achieve, and whenever possible, try to use heat exchangers instead of utilities. So try and somehow to integrate this, all these heating loads. Okay, so what would be a good approach here? Let's think. Let's see. Maybe I could, this guy needs 100. This guy has 100 to give. This guy needs 100. Sorry, this guy has 160 to give. This guy needs 180, right? So I could use some of this energy to heat up this guy. I could use maybe some of this energy to heat up this guy. And then whatever is left, heating or cooling, I can add a small cooler or a small heat exchanger just to make up the balance, right? And if I look at this 162 to 100, then maybe I'll have 60 left. Maybe I can add a small cooler. 160 to 180, and then I'll have about 20 left. Maybe I can add a small heater. Something like that sort of makes sense. Okay, let's have a look at this design. And this is what we did, right? So let's have a look here. What happened? Yeah, so the stream at the bottom, which I needed to heat from, or cool, sorry, from 130 to 40, and this stream, which I needed to heat from 30 to 20, I integrated them into one. So if I look here, instead of having these, so in this case, I linked this guy with this guy. And instead of having two heat exchangers, I just had one heat exchanger. And the remaining utility, I just added a small cooler here. And on this side, I did the same thing. So the stream which had to be cooled from 180 to 80, I linked it up with the stream which had to be basically heated from 60 to 100, right? So this guy starts at 60 here, enters this guy at 60 here. It leaves at some temperature, but this allows the stream to cool from 180 to 80. And then I need to make up for this utility left. So I add a small heat exchanger to complete the heating up to 100, right? So this achieves some sort of integration right here. I have 4 units, right? I use 60 kilowatts of steam and 18 kilowatts of cooling water. So, I mean, this is the sort of thing you can do haphazardly, right? Just trying to match them, match the sources in the sink without any sort of systematic approach, right? So I could have matched the other two legs of hot and cold streams. So, however, is there a way for you to know, is this optimal? Is this the best solution you have? Let's have a look. Let's try to formulate a way. So in order to do this, we need to build something. In order to find out whether it's optimal or not, we need to build something called the temperature enthalpy diagram, okay? And we're gonna talk about it in a second in more details, but the idea is that, you know, I need to transfer all the information I have into a graphical diagram. And in this graphical diagram, I'm plotting the initial temperature, the final temperature of my hot streams, initial temperature, final temperature of my cold streams, and then I'm able to see clearly the heating and the cooling utilities, okay? And you can do it for whether you want to heat or cool, whatever it is. And what this allows you to achieve is that you achieve a correlation between delta T minimum, the minimum heating utility required, and the minimum cooling utility required, right? So let's have a look at an example. So in this case, I have 3 hot streams. So let's say you're given an example where you have 3 hot streams. The first step is always to plot your hot streams onto this table, right? So let's say you're given, so let's have a look here. You have stream A, sorry, you have 3 streams going from, what's the best way to say this? Okay, let's have a look here. So you're usually given, so you have your table, right? Which is what we had before. Here we go. I have H1, H2, H3. I have, you know, this is my source temperatures, T source, T target, stream name. And I usually have a CP value right here, right? And then you have, let's say, T1, T2, T3, T4, T5, T6. It doesn't matter. But the idea is this. So let's look at, so first of all, I look at stream H1, right? So stream H1 is moving from T1 to T4. Okay, so I just go here, stream 1, I drop its starting point anywhere, T1, and then I draw its final point to T4, right? In this case, it's T2 to T5. Let's write these temperatures to match. So this stream from T2 to T5, let me write it here. No, I need the pen. Okay, let's write this guy here. So this is T2 to T5. This is, let's say, T1 to T3. And the last one is from T2 to T4, right? So you're given 3 streams, you're given some stream information, and we want to build what's called a composite curve. And the first step in building a composite curve, is to build this thing called the temperature enthalpy diagram. So this is what we're doing here. So what the procedure is basically just look at the table, you draw a line at each temperature. So this is what I did. So I have T1, T2, T3, T4, T5, and I just drew a line at every temperature point, and then I just basically drew, or dropped my starting point here and dropped my final point here for these 3 streams, right? So stream H1 from T2 to T5, I just indicated this point here and this point here. H2 is from T1 to T3, and H3 is from T2 to T4, right? Okay, so you need to draw 3 lines between these 2 temperatures for each of these streams, and these lines need to have a slope, and the slope of these lines will be equal to your CP value, right? So this is, so from T1 to T3, this was CP, in this case was B. From T2 to T5, CP was A, and from T2 to T4, CP was C. That sort of makes sense the more you practice it. I know here doesn't make sense or it's confusing or whatever, but you really need to practice a couple of examples to do it. And this is what we'll do in the homework. We'll practice a few examples. And it's a very logical approach. You just follow the steps, you'll get the result you want. So let's recap. So we said you have your stream table. First step is to just indicate where your temperatures are. So, you know, in some cases you might have 9 streams, whatever it is. You just draw lines in all of these next to all of the temperature points you have. And then you look at them stream by stream. So H1 goes from T2 to T5. So H1, I start at T2, and then I draw a line to T5, and this line has a slope equivalent to the CP value. H2 goes from T1 to T3, so I go to T1, and I draw a line to T3 with a slope equal to this heat capacity, mass heat capacity. And then H3 goes from T2 to T4, so I go to T4, and I draw a line from T2 to T4 with a slope equal to the mass heat capacity, okay? And where do you draw these lines? We're gonna get to it in a second. You know, once we practice a bit, you'll start seeing it in a better way. Okay, but realistically, it doesn't matter where you draw any of these lines, okay? What you really want to have is you want to have your lowest temperature at the absolute left and your highest temperature at the absolute right. This is good practice, but you know, practically it won't matter, okay? And we'll see it in a second. So after I draw the 3 lines, I need to calculate the enthalpy in each of these temperature intervals, right? And the delta H interval refers to the distance between the temperatures, any 2 temperatures I have in this table, right? These 2 temperatures don't need to belong to the same stream. As long as they're somewhere in this table, this is considered the temperature interval. And again, if I'm calculating the delta H in this interval, right? Delta H, you recall, delta H is equal to let me get the pen here. So delta H in this case is equal to CP delta T, right? If I have more than one CP, it will be equal to summation of CP delta T, and I need to keep an eye out for this parameter here. So if I look at this interval, the delta H is just, I only have one heat capacity, which is B, so CP is B, multiplied by delta T, which is T1 minus T2, right? If I calculate the delta H in this interval, so my delta T is T2 minus, right, T2 minus T3, and my CP is just a summation of all these 3 in this interval. So in this interval, I have A, I have B, and I have C. So this is the delta H interval. In this interval, the delta T is T3 minus T4, and my CP is just A plus C. And in this final interval here, my delta T is T4 minus T5, and I only have one CP, which is A, right? So I can calculate really all my delta H intervals required. So once I've done this, what I'm gonna do now is I'm gonna link, right? I'm gonna link this figure together. I'm gonna connect them. It's from being 3 lines into being 1 line. And the way to do it is you start from your lowest point on the left-hand side, your lowest temperature, and I look at the slopes. So you need to keep an eye out on the slopes here. So in this interval, the slope is A. So I just draw a line from here to T4 with a slope of A, and then from T4 to T3, the slope is A plus C. So I need to draw a second line in this case with a slope of A plus C, right, to this interval. And then between T3 and T2, the slope is A plus B plus C. So I need to draw a line with a slope of A plus B plus C up until T2. And then finally T2, the slope is only B. So I draw a line with a slope of B all the way to T1, right? So what I did in this case, I just linked the 3 lines into 1 line, and this is called the hot composite curve, right? And this is what is shown here. So what I did is I basically just connected these lines by looking at the summation of CP at each interval. Okay, so let's have a look at an example. So let's go back to the example we have. If you recall, we said let's do the hot composite curve. So I have two hot streams, right? I have H1. It's going from 180 to 80 with a CP of 1, and then I have H2 going from 130 to 40, and this has a CP of 2. And this was given a few slides ago, right? If you recall, it's right here. So H1 180 to 80, CP of 1, H2 130 to 40, CP of 2. Okay, so let's apply what we just said. So what I want to do is I want to plot basically this figure right here. I need to plot T versus Q. So first step, we said we're gonna draw lines next to the temperatures. So I have 4 temperatures in this case. I have 40 here, and this is not to scale, just to give you an idea. Then I have 80. And then I have 130, let's say 130 is here. And then finally I have 180. Okay, so these are, first step, I just draw dashed lines, or maybe just make a mental note of the 4 temperatures, and then I'm gonna draw these lines, right? So first stream goes from 180 to 80 with a slope of 1. So I draw the first line, I start at 180, I draw a line with a slope of 1 down to 80 right here, and this line has a CP equal to 1. And then I draw the second line from 130 to 40 with a slope of 2. So I go start at 130, and I draw anywhere, it doesn't matter. I know it looks a bit strange, but this is, just draw it on your figure from 130 to 40 with a slope of 2, right? So I draw my 2 lines, and now I look at my intervals here. So this is my delta H interval. So in my first interval, my delta T is 180 minus 30, and my CP is equal, so summation of CP in this case is 1. In this interval, summation of CP is equal to 3, and in this interval, summation of CP is equal to 2. So once I'm done with this, I need to redraw, I need to reconnect these, or I need to basically combine these lines into one line, which will be my overall composite curve. So if I start, let's start here. In this region, I need to draw a line with a slope of 2, so I just draw a line with a slope of 2. In this interval, I need to draw a line with a slope of 3, so I'm just going to draw a line with a slope of 3. And then in this interval, I need to draw a line with a slope of 1, so I draw a line with a slope of 1. And this becomes my hot composite curve, right? And this is called a hot composite curve. Okay, so this is the approach to do it. And if you have a look here, so I have CP1, I basically, draw dashed lines, or maybe whichever way you want to do it. If using Excel, you can just find a way. Find your temperature, all the temperatures listed in this table, to form the boundaries of your temperature intervals. So in this case, there are 180, 80, 130, 40, 180, 130, 80, 40, and I just draw my streams from the starting point to the final point with a slope equivalent to the CP value. So this is H1, this is H2, and I take note of the delta H, or basically what's more important is summation of CP, right? Of course, you can do it using delta H if you want. So if you want, instead of really trying to draw the slope, I can calculate the delta H and then go, okay, this is my starting point here. So I need to move by a delta H of this much, and I drop the second point, and I can need to move by delta H of this much, drop the second point by delta H of this much, drop the third point. Whichever way is simpler, whichever way works for you. I find the slopes one works better if you're using graphing sheet. Maybe delta H1 works better if you're using Excel. whichever works. So basically what happens after I do this, I'm gonna combine all of these. I'm gonna combine these two lines this way. So I combine these two lines in this manner right here. Let me erase. And when I combine them, I look at each interval, I look at the slope, so maybe I look at delta H, whatever it is, and I combine them in this manner. So I start from here. And again, this delta H refers to this. So this delta H is equal to 80. This delta H is equal to 150. And this delta H is equal to. And it's important to note that this bottom, you can, of course, you can start from 0 if you want, but this bottom doesn't really have any points. You can add a reference unit, you can add a reference point, which is 0 to everyone, but heat exchange is, you need to understand that heat exchange is, it's a relative quantity, right? So you can always add a reference point for it to make sense. And of course, you're using graphing sheet, using Excel or whatever, you should always add a reference point, okay? And this is the approach we're using, and this creates this curve called the hot composite curve. Okay, for the cooled composite, same approach, okay? For the very same identical approach for the cooled composite. So let's do it here manually. So I have two cooled streams. I have C1, which goes from 30 to 120, and we said the CP in this case is 1.8, right? So this is T source, T target, this is CP. And then I have a second cooled stream here being heated from 60 to 100 with a CP of 4. Okay, so again, first step is I'm going to create, or in a graphing sheet, I have my temperature, I have my Q, and I'm going to just define my temperature intervals. So I have my lowest temperature in this case is 30. So let me just draw here 30. Second one is 60. 60. Third one is 120, is a bit of a jump, or third one is 100 actually, so be careful. So it'll be 100. And then final one is 120. Right here, 120. Okay, once I've done this, I'm gonna plot the two streams. So my first stream goes from 30 to 120 with a CP of 1.8. So it starts at 30 and I end at 120 right here. And I start at 30 and I draw a line with a slope of 1.8 up to the 120 line, right? So this will be my first line, right? Alternatively, if you don't want to use the slope business, you can calculate the delta H, right? And you can basically gauge the delta H from here, right? So this will be your delta H1. So this might be easier, but just whichever, both ways are the same. CP 1.8. Let me plot the second line here. I go from 60 to 100, so I start at 60, and I need to go to 100, and this line will have a slope of 4. Alternatively, delta H in this case is what, 160. Alternatively, I can just start here and then move by 160, and then find the second point and draw my second line. Both ways are the same. CP is 4. Okay, so once I get to this point, now I need to take a look at my intervals here. So summation of CP here is 1.8. You can also use delta H. Summation of CP here is 5.8. Summation of CP here is 1.8. So my composite curve in this case I'm going to start at my lower interval here. You can start anywhere. You can erase them and redraw them. You can open a new Excel tab or a new graphing sheet, doesn't matter. Start here, I need to have a line with a slope of 1.8 between these two intervals. I need to have a line with a slope of 4 between these two intervals, and then I need to have a line with a slope of 1.8 again between these two intervals. And this becomes what's called my cooled composite, right? So this is my cooled composite line, okay? So again, same idea. I define my intervals, temperature intervals. I calculate my delta H, or I know my slope. I draw a line with this slope, with this delta H for both streams. And then I look at the delta H, or alternatively, I look at the summation of CP. And I just connect them to get my cooled composite curve. Okay, and this is called the cooled composite curve. So let's say, so I give you a bunch of information. You draw your hot composite curve, you draw your cooled composite curve. What do we do now? Okay, now you put both figures on the same diagram. Okay, so after drawing your hot composite and drawing your cooled composite, you're going to replicate them on the same diagram. Okay, so I drew my hot composite here, I drew my cooled composite here originally, and after drawing them on the same diagram, you need to take note of the temperatures between them, right? So I need to keep an eye out for this temperature right here. Let me change the color, something else. Green, okay. So I need to look at this temperature. I need to look at basically just the temperature between the two lines, right? And the temperature, of course, is the vertical distance, not the horizontal distance. And I need to move my cooled composite until the temperature between these, or the minimum temperature or the minimum distance point, is equivalent to my delta T minimum, okay? And this is very important. So first of all, I just drop them randomly, the hot composite and the cooled composite on a figure, and then I move my cooled composite closer to my hot composite until the minimum distance between them corresponds to my delta T minimum, okay? And once I achieve this, the difference in enthalpy between the endpoint or the tail of the hot composite and the head of the cooled composite, this is my minimum heating utility. And this distance right here between the head of the hot composite and the tail of the cooled composite is my QC minimum here. Okay, so let me reiterate this point. You drew your hot composite, or you drew your cooled composite. Now you draw them, you drop them both on the same figure, or draw them both on the same figure, whatever you want. And then after drawing them both on the same figure, I start moving my cooled composite until the minimum distance between the two lines corresponds to delta T minimum. And again, this is the horizontal distance. Once I have them configured such that the minimum distance between them is equivalent to delta T minimum, I look at the distance between the tail of the hot composite and the head of the cooled composite. This is my minimum heating utility. And I also look at the distance between the head of the hot composite and the tail of the cooled composite. And this is my minimum cooling utility. Very important. And if we do it for the example we're just looking at, this is what it is. So this is our hot composite. This is our cooled composite. And our your T pinch or pinch temperature was 70. We're gonna find out how to really find the pinch temperature mathematically, but graphically, the way to find the pinch temperature is to basically look at the pinch temperature is the temperature at which you have a delta T minimum, right? So delta T minimum in this case was 10, right? So in this case, delta T minimum was 10. And the point at which I achieved this delta T minimum was between 60 and 70. So this is my pinch point where the hot pinch is 70 and the cold pinch is 60. And the hot pinch is basically the upper limit, cold pinch is the lower limit. So graphically, once you move them together, once you move them closer together, once you get to the point where you achieve delta T minimum, then this becomes your hot pinch and this becomes your cold pinch, okay? And this is what we have in this case. And then you determine your minimum heating, your minimum cooling utility. So we said the minimum cooling utility is just this distance right here. So this is your minimum cooling utility. And on the other side, the minimum heating utility is this distance right here, and this is the minimum heating utility. So in this example, the minimum cooling utility was 6, and the minimum heating utility was 48. And these are referred to your maximum energy recovery targets, right? So this design is the optimal design. It does not violate any thermodynamics because I still have my delta T minimum driving force. I'm using up all the heat from both, or as much heat as possible from both the hot and the cold streams. And I have my And then I determine my cold utility, minimum cold utility, and minimum heating utility. Okay. So this point is called the pinch, which is the distance at which I have a delta T minimum. And what does this mean really? Pinch. So what does it mean? So the pinch basically, or the idea of the pinch, it's you're separating your heat exchanger network into two parts. Separating into a heat sink above the pinch, at which QH minimum utility must be used. So this part here is your heat sink. And then your heat source below the pinch, where at least QC minimum utility can be used. And this is your heat source. And if you get comfortable with designing heat exchangers, this starts making more sense. Or if you took advanced, if you end up doing some graduate course in thermodynamics or whatever, or you end up being, a gas compression engineer or something like that, the idea of a heat source and a heat sink starts making more sense. And if you divide your problem to a heat source and a heat sink, you're minimizing chances of errors. You're sort of focusing on the parameters which matter. Okay, and if I divide it into a heat source and a heat sink, this just allows me to split the problem and minimize any possible errors you could do mathematically. Okay, and of course, what this slide says, if I add some heat, I can always shift my heat sink problem to the left or shift my heat source problem to the right. This becomes more clear once we deal with the algebraic method, but for now, just take note of it mentally, but don't worry about it much. Okay. Significance of the pinch. This is an extremely important slide. You need to remember this. Same way you remember first law of thermodynamics, you cannot forget these rules because they govern everything you do. So, significance of the pinch, you should never transfer heat across the pinch, okay? This will make more sense later on. You should never use cold utilities above the pinch. So if you recall, pinch point, 2 lines, okay? Here it's QH, here it's QC. Never use cold utilities here, never use hot utilities here. This is very important. Please don't forget this. Please don't make these mistakes. This is a very common type of mistake where, my system doesn't match, let me use cold utilities over the pinch. If the math doesn't work out or if you don't find the right pairs, this means you did something wrong with your composite curve or something like that, but you should never use cold utilities over the pinch or hot utilities below the pinch for the simple reason that thermodynamically, it does not make sense, right? You're going to end up with some very strange cold utility or something thermodynamically improbable. Okay. So this, so now let's try to introduce a second sort of idea, which is the algebraic targeting method. And what we're doing with this algebraic targeting method, we're doing the same thing as we did with drawing the composite curve, but we're doing it algebraically. Because sometimes it's not always convenient to really draw a bunch of sketches, replicate the sketches a bunch of times. It's not very convenient to do it. It's not very practical for you as an engineer to do it. So we need to translate all of this fancy stuff into an algebraic cooled method to do it. Okay, so before doing it, I'm going to define a few temperatures or a few parameters. The hot temperatures will be capital T, the cool temperatures will be small t, and I have thermal equilibrium when T equals to small t. However, in a heat exchanger, you don't want to have thermal equilibrium because at the point of thermal equilibrium, the heat driving force is 0, right? Heat. Right, because if I have, let's say, 2 walls and they're both at the same temperature, there is no driving force, there's no incentive for heat to move around. But if this is a 30, there's a driving force for heat to jump this way. If this is 90, right, there's a incentive for the heat to move, right? So you always need to have this temperature driving force called delta T minimum, and subtracting delta T minimum from the hot temperatures will ensure thermal feasibility at all times, okay? So when dealing with the algebraic method, we always subtract delta T minimum from the hot temperatures, and once we practice one example, it makes sense, but always keep this in mind. When you're doing algebraic targeting method, I always need to correct my hot streams for the delta t minimum. And this is sort of the algebra of this targeting method. You can go through it if you're interested, you really want to have a look, but you're basically building a small heat balancer in every step and just making them all make sense. So don't worry about it. Just learn the procedure, and we'll get to it in a second. Okay. And then heat balance. So this is just for your reference. You can always have a look at it later, but we don't need to worry about it for now. Okay. In the algebraic targeting method, what we really need to build, we need to build something called the energy cascade, the enthalpy cascade. And of course, these are just some pointers for you. There's also the book, but you just need to be aware that in your enthalpy cascade, your enthalpy cascade becomes feasible, when I don't have any negative number, right? Where my lowest number is basically a 0, and we're gonna get to it in a second, or maybe next lecture. And you basically revise your enthalpy cascade for it to make sense. Okay, so just read through these slides. Read through this theoretical thing just for your knowledge. We won't really get to it. I mean, when I took this as an undergrad a bunch of years ago, it zipped right out of my head. Next second, you never really use it. But what really needs to stick with you is the procedure on how to build the graphical method for building your composite curves, determining your QC-min, QH-min, and your algebraic method, the procedure as well for building your enthalpy cascade. So let's have a look at an example, and we'll just go through this example and follow these steps. And really, you need to know these steps for everything you do in terms of algebraic targeting. Okay, the steps will always be the same. So you're given an example. I have 2 hot streams and 2 cold streams, and the delta T minimum is 10 degrees Fahrenheit. Let's just have a look at these streams. H1, H2, C1, C2. H1, I need to cool it from 260 to 160, has a CP of 30. H2, I need to cool it from 250 to 130, has a CP of 15. C1, I need to heat it from 120 to 235, has a CP of 20. And C2, I need to heat it from 180 to 240 and has a CP of 40. Okay, so given some information, or you're given a figure and you extract this information. And again, this step or this part is the same whether you're doing graphical or algebraic. Don't start anything until you have this table, right? If something is missing, you can't really move forward. So I have this table. What's step 1 in the algebraic targeting method? Step 1, always subtract delta T minimum from the hot temperatures, okay? Step 1 always applies. Subtract delta T minimum from the hot temperatures, okay? Learn these steps, very important. This is what I'm gonna do. And by hot temperatures, I mean this temperature, this temperature, this temperature, this temperature. Temperatures of the hot streams. I don't mean the target temperature of the cold, no. I just mean all the temperatures for the hot streams. And this is what happens here. I subtract delta T minimum. 260 becomes 250, 250, 240, 160, 150, 130, 120. Subtracted temperatures. Okay, this is what we did. Good. So now what do we do? So step 1. Step 2 right here. I need to build my interval heat balances. Okay. And what this means is I'm gonna calculate the enthalpy for each temperature interval. Okay, so for each temperature interval, I'm gonna calculate the enthalpy load. And this corresponds to the part where, remember when doing the graphical method, I just listed all my temperatures, and then, after drawing the lines, whatever, I calculated the delta H, or I calculated the delta CP, right? Delta CP multiplied by delta T. And this corresponds to this. So for each interval, I'm gonna calculate my enthalpy load. So again, let's have a look here. So I divided my table into, so first step, I divided my table into temperature intervals. So let's have a look here. So first of all, we subtracted 10. So this became 250. This became 150. This became 240. and this became 120, right? This was step one. Subtract delta T minimum from all your temperature. And then now I'm gonna arrange them from highest to lowest. So I need to arrange, so in order to determine my temperature intervals, I need to arrange all these temperatures from highest to lowest. So so my highest temperature here is, 250. My second highest temperature is 240, sorry. My third highest temperature is 235. Then I have 180, and I have a 150, right? There's 150, this guy right here. And finally, I have a 120. And when doing this, when arranging your temperature intervals, it's very, very common, or a very common error to just drop one of the numbers, right? This is a very common error. So at this point, please always double check your calculations, okay? So this is what I did. I drew these temperatures right here. So now how many intervals do I have? I have one interval, 2, 3, 4, 5. So I have 5 intervals, right? So these are basically my temperatures, and these are, so this is my interval number right here. 1, 2, 3, 4, 5. Okay, so in each interval, I'm gonna do one thing. I'm gonna, here at the top, I'm just gonna list my streams, H1, H2, H3, H4, and then I'm gonna just draw a dashed line next to each temperature, right? Just to clearly define the boundaries of each interval. This is what I'm doing. Good. Let me change this pointer. Oh, let's go. Super. Okay. So again, first of all, I arranged my temperatures from highest to lowest. I determined my intervals, and then I just listed my stream numbers here at the top. And under each stream, I'm gonna just draw a straight line from the start to the end. So H1 goes from 250 to 150. So this is H1 right here. It goes from 250 to 150. H2 goes from 240 to 120. H2 goes from 240 all the way down to 120. H3, sorry, C1, right? C1, C2. C1 goes from 120 to 235. So C1 goes from here all the way to here. And C2 goes from 180 to 240. C2 goes from 180 to 240. Okay, so now I clearly see my intervals, and I clearly see how my streams cross these intervals. So after doing this, next step is to calculate summation of CP in each interval, right? So if I look here in this interval, I only have one stream H1. Yeah, one thing you need to keep or know at this point is your summation of CP, you're not just adding. Let me rephrase this equation. I need to calculate this parameter called, or your summation of CP in this case is equal to summation of CP hot minus summation of CP cold. Need to remember this. Summation CP hot minus CP cold. And this is what I'm going to calculate in this column right here. So if I look at this interval H1, I only have one hot stream, and the CP is 30. So this parameter is 30. And this number can be negative, so it's fine. In this interval here, I have H1 and H2, two hot streams, 30 plus 15. So this is what, 45 minus one cold stream, which is C2, which is 40. So this is equal to 5, right? In this interval 3 right here, I have two hot streams and two cool streams. So I'm just adding the two hot streams, 45, subtracting the two cool streams, 60. So in this case, it's minus 15. In this interval right here, I have two hot streams, 45, subtracting the CP of the cold stream C1 minus 20. So this is 25, right? Just 45, 30 plus 15 minus 20. And the last stream, I have one hot stream, which is H2, 15, minus one cold stream, which is C1, 20. So this guy is minus 5. Okay, so once I get to this point, I have my summation of CPs, and I reach this point. Okay, so so next step would be to calculate your enthalpies, but let's go through the slides for now. And this is what this slide shows you. So I have my H1, H2, did I miss the temperature? 250, 240, 235, 250, 240, 235, 180, 150, 120. Okay, so they just added one at the bottom, which is 6, doesn't matter. You can follow this approach or follow my approach, it's up to you. They both give you the same answer. So anyways, so that's what we did, calculated summation of CP hot minus summation of CP cold. And once you do this, you calculate the delta H, right? Which is just the multiplication of summation of CP hot minus CP cold multiplied by delta T. If you look at what we did here, so if I calculate delta H here, this is going to be 30 multiplied by 10, 300, 5 multiplied by 5, 25, minus 15 multiplied by, this is what, 55. So this will give you minus 825, 25 by 30, 750, and minus 5 by 30, which is 150. Okay. So build your table, build your intervals, all this stuff. Get your summation of CP hot minus CP cold, get your delta H. And this is very important. Once you get to this point, you're about 20% through, but at least this is the point where you can really check your math. Double check your math, see if everything makes sense, see you don't have any wonky numbers, nothing strange, whatever it is. And after you do this, you're going to go to step 3. We're going to build what's called an enthalpy cascade. So how do you do an enthalpy cascade? What does it mean? And this is what it is, right? Basically, the easiest way to do it is to just T1 250, right? T2 240, and I have this. I have a heat exchange point here, and then I have this, right? And here I have my delta H1, which is 300. And this is what's shown here. So I just list my temperatures, and then between within each temperature interval, or between each two adjacent temperatures, I just draw a square. I write my enthalpy in it all the way to the bottom. And then once I'm done with this, I'm gonna just add up all my heat, all my enthalpies. So QH at the top is 0, there's nothing added. 0 plus 300 is 300. Sorry, 300 plus 25 is 325. 325 minus 825 is minus 500. Minus 500 plus 750 is 250. 250 minus 150 is 100, right? So again, first step, I just write my intervals. I draw a box between each interval. In this box, I just write my enthalpy. And then starting from 0 at the very top, QH equals 0, I just start adding up the enthalpies and writing them, under each box or next to the next interval point, right? I just write all my Q's right here. And at this point, what you're looking for the most negative Q, right? You're looking for the most negative residual in this case. And in this case, the most negative residual is minus 500. Sometimes it's positive. It doesn't matter. Just look at the most negative or your lowest residual, right? If it's not negative, lowest. Some cases, all of them are positive, right? Maybe I only need cooling or something, right? Doesn't matter. If all of them are positive, just find the lowest one. It doesn't matter, okay? So find your most, but in conventional cases, we're gonna find the most negative residual. And at this most negative residual, I'm gonna add enough heat at the top of this cascade so that this is 0. So if you think cascade, basically if I add something from the top here, it's just going to cascade all the way to the bottom. So I need to add enough energy to this process so that this reaches 0. And in this case, I added 500 because it's minus 500. If I add 500 to the top and then 500 plus 300, 800, all the way 800 minus 825 is 0. And then you just do your math and then you get to the very bottom at QC right here. And once I add this heat, the point at which I have a 0, this is my cooled pinch, very important. The top here, the amount of heat I needed to add to get this 0 is my minimum heating utility, and the point at the residual heat remaining at the bottom is my minimum cooling utility. Okay, and this is really the end of your cascade method or enthalpy cascade. Let's have a look again. Let's just go through these steps one more time before we end this lecture. You're given a bunch of data for hot streams, cold streams, whatever. Step number 1, I'm gonna subtract my minimum temperature from my hot temperatures, right? To get the updated temperature table, basically. So step number 1, I just subtract my delta T minimum from my hot streams to get an updated table. Step number 2, I'm gonna arrange these temperatures from hottest to coldest, right? So I'm gonna arrange them. And between each 2 temperatures, I'll have an interval, right? So this is interval 1. This is interval 2, interval 3, interval 4, interval 5. And just list your, and then after doing this, I'm gonna write H1, H2, H3, C1, C2, all the way to the end. Then I'm gonna draw a line from the start of each interval, from the starting point to the end point. This way, you can do it in a table, you know, books like to do it in tables. This is the method, this is the easiest method to visualize, at least for me, and you know, I think it's the easier way to do it. So you just draw your starting point, your end point, and then in each interval, I'm going to calculate the summation of Cp hot minus Cp cold by looking at which streams are available in this interval. So this interval, I only have H1, look at Cp hot stream, so 30. This stream, I have 2 hot streams, Cp of 30, Cp 15, 1 cold stream, Cp 20. I do my math, calculate the summation of Cp hot minus the summation of Cp cold. Once I get this parameter, I'm going to calculate my delta H. So this is what happens here. So I get my, so list them from hottest to coldest. Delta T, of course, you need to know this. So you can write it down. Calculate summation of Cp hot minus Cp cold. Calculate your enthalpy. Once I get to this point, I'm going to translate this table into a cascade diagram. And this is what we do here. So I'm going to translate this table. Let me erase all this junk. So I'm going to translate it to a cascade diagram. And again, the idea of a cascade diagram, you just start with your, you just draw lines for the intervals. And between each interval, I'm just going to draw a box with my delta H. And this, you just follow the procedure. Do it. It's algebraic systematic approach. You just follow the steps, get your numbers. I do this, and then just connect them with arrows. And then I start at the very top with QH equals 0. And then I start adding up the heat. So 0 plus 300, 300, 325, 325, all the way to the bottom. And then once I'm done with this, I look at these Qs and I try to find the most negative Q, right? Most negative Q, not the most negative enthalpy, most negative heat. Once you get to this, once you find this most negative heat, I'm gonna add energy at the top so that this point is 0. So in this case, it was minus 500. I added 500 at the top so that this point moves from minus 500 to 0. And once you do this, this point becomes your pinch point. So this is your cold pinch, 180. And your minimum heating utility is how much heat you add at the top. And your minimum cooling utility is how much heat remains at the bottom. And homework number 3 will really focus on these types of approaches, algebraic, graphical. On your exam, expect to do 1 algebraic, 1 graphical, and just get comfortable with the steps. And again, this is no intelligent, there's no like, you don't really need to think about anything. You don't try to overthink it, think outside the box. It's not sort of a problem solving intelligence type of problem. This is sort of a following the steps, similar to when you're designing a safety relief valve, right? Just follow the steps, get your numbers, and these numbers will be what you need for your design metrics, right? And again, most of your design approaches are based on systematic algebraic methods. Okay, so this is the end of this lecture. It's a bit of a long lecture. but this is a very important milestone in this course. You should be able to compute pinch temperatures using the two approaches. You should be able to build your composite diagram, and you should be able to compute your maximum energy recovery targets using both graphical and algebraic methods. Okay, there will be a second video posted for homework number 3. Next lecture will also be practicing these types of problems, and we also have sort of a review lecture before the test. And of course, if you have any questions, come to office hours, send me an email, just don't hesitate to reach out, and you're gonna get comfortable with this eventually. Thank you so much.